Today I'm reviewing instance-dependent early stopping, or IES, a method that pushes early stopping down to the granularity of individual samples. Traditional early stopping waits for the overall validation curve to stop improving so that if it reaches certain saturation point, so that if we see it overfits, the early stopping kicks in and the training stops for a whole data set all at once. But something we need to note here is that individual samples learn at different speed. Some flatten early, which means they learn quickly than others, and others remain difficult, which means they learn in more slower pace. Still, we keep back propagating on all of them every epoch. That is the inefficiency this instance-dependent early stopping is trying to remove. So let's move on to the core idea. IES doesn't check whether a sample's loss is small or getting smaller. It checks whether its loss curve has stopped curving. It uses something called the second order difference. And the following is the equation. Second order difference of the loss is literally the difference of differences, delta of deltas. You first measure how the loss changed between epoch t and t minus 1, then how it changed between t minus 1 and t minus 2, and the equation takes the difference between those two changes. So we need 3 consecutive epochs, t minus 1, t minus 2, to calculate, to compute this second order difference. So what it shows you is that if this value is close to 0, it means the change itself has stopped changing. The loss curve has flattened and the model is no longer improving in that sample. The model has stopped learning new information from that sample. So the paper says if this second order difference is smaller than some hyperparameter delta, the sample is marked as mastered. This is more stable than just thresholding the raw loss because the curvature directly reflects learning progress. Let's see at the algorithm really quickly. It is really straightforward. First, compute per sample losses each epoch. And when they reach more than 3 epochs, compute their second order differences, all to the granularity in per sample level. 3. Identify mastered samples. If it is smaller than delta, the second order difference is smaller than delta, then you consider it mastered. And remove them from the next epoch's training set. And repeat until all samples are mastered or normal early stopping kicks in. And as training continues, the dataset automatically shrinks because the master samples are being removed, and the model focuses more on the difficult examples. So why this helps? Removing easy samples first saves backprop computation cost, and second, sharpens gradient updates. Third, keeps training focused where it matters. The method is simple but shifts the training dynamics meaningfully. Less repeated work and same final performance. And why do I say that same final performance? The result is in here. So the gray highlighted area shows the no removal model and its test accuracy, while the line curve, the red line, shows the IES model's test accuracy in both CIFAR10 dataset and ImageNet 1K dataset. So IES matches the baseline accuracy almost perfectly if you can see the top 2 figures and bottom. Yet, over time, IES excludes a huge portion of the dataset from training, so IES delivers the same accuracy while using significantly fewer effective samples than the traditional early stopping. So instance-dependent early stopping is a small change in perspective, but it makes training smarter and more efficient while maintaining the same accuracy. Yeah, that was the gist. See you next time.